This lesson deals with supplemental problem 12.4. You can find this problem in the ECE202 ebook in the Chapter 12 supplemental problem starting on page 9. Most speakers cannot reproduce the entire audio range of 20 Hz to 20 kHz. So we have speakers that cover part of that range. Woofers are speakers that can reproduce tones in the lower end of the audio band, typically from 20 Hz to about 750 Hz. Mid-range or mid-woofers are speakers that can reproduce typically between 750 Hz and 6 kHz. And lastly, tweeters are speakers that can reproduce the upper end of the audio band from roughly 6 kHz to 20 kHz. It'll be necessary to split up the frequencies of our output and give those to each of the speakers. Given, say, a left channel, I'm going to take it and feed it to 3 filters, one to do the low end, one to do the mid, and one to do the high. Shown here is a transfer function. We're going to let low frequencies below, say, 750 pass, and above it begin to attenuate them. Then for this speaker, letting everything pass roughly between 750 and 6 kHz. And then for the tweeter, letting everything pass above 6 kHz. We do something similar also for the right channel. The filters that are used to separate this audio band, the frequencies, are called crossover filters. I'd like you to use the following circuit for the low-pass crossover filter using an L and a C, and the R will be our speaker, or an approximation to it. Now, to be able to design the circuit to pick the L and C, we'll need to solve for V out of S over V in of S, and then use that to solve for H0, omega naught, and Q naught. For the high-pass crossover filter, I'd like you to use this circuit where we're going to interchange the L and the C, and again, need to solve for V out over V in of S, and then use that to find H0, omega naught, and Q naught. Then I'm going to have you combine these two filters and make a bandpass filter, and do the same thing. I'd also like you to prove the following statement. For a second-order low-pass or high-pass filter, if Q naught is equal to 1 over the square root of 2, which is equal to 0.707, then the magnitude of the gain is down 3 dB at omega equals omega naught. Lastly, the impedance of a speaker varies with frequency. We can approximately treat an 8 ohm speaker as an 8 ohm resistance, but it is an approximation. I'd like you to design and simulate your low-pass and high-pass filters using L's and C's that are in the following ranges. For the inductances between 100 microhenries and 100 millihenries, and for the capacitances between 100 picofarads and 100 microfarads. Let's begin by analyzing the low-pass crossover filter. I have a voltage divider with these two elements in parallel, voltage dividing with SL. Let's take the impedance of this parallel combination as the product over the sum of their impedances. So 1 over SC times R divided by R plus 1 over SC. And that's going to voltage divide with SL times Vn will give me V out. That's my transfer function. Let's take this numerator term and multiply numerator and denominator by SC, so I get R, SCR plus 1, and then the same thing for this term. Let's multiply numerator and denominator by SCR plus 1, and that's going to cancel this term, so I just get R, and then I have an R term here, and then SCR plus 1 times SL will be S squared LCR plus SL. Let's rearrange the denominator by powers of S, so I have S squared times LCR plus SL plus R. Let's divide the numerator and denominator by LCR. That'll give me a numerator with just LC, a 1 for this term, and then L divided by LCR will just give me a 1 over RC times S, and then R divided by LCR would just be 1 over LC. Now, is this the form of a low-pass filter? And the answer is yes. We have something without S in it, and we have an S squared times 1, something times S, and something with S to the 0. Comparing terms, this would then be our omega naught squared, so omega naught is 1 over the square root of LC. The term in the numerator is H0 omega naught squared. We know what omega naught is, so let's divide by omega naught squared. The term in the numerator is equal to 1 over LC, and then squaring this term, we get a 1 over LC. They cancel, and we just get a value of 1. The value of Q naught is here, so let's take the reciprocal of this, which is Q naught over omega naught, and multiply that by omega naught. So the reciprocal of this term would just be RC, and omega naught is 1 over the square root of LC. If you write this C as the square root of C squared, then we get a cancellation with one of these with this. And that gives us a value of Q naught equal to R square root of C over L. Next, let's analyze the high-pass crossover filter. And again, I have a voltage divider with this L and R in parallel, voltage divided with a capacitor. So the impedance would be the product over the sum of the impedances, SL times R over SL plus R, voltage divided with 1 over SC. Multiply numerator and denominator by SL plus R. It gives me an SLR in the numerator, an SLR for this term, and then 1 over SC times SL plus R. Let's multiply numerator and denominator by SC. That will then give me an S squared LCR, S squared LCR, 1 times SL, and then 1 times R. Then let's divide numerator and denominator by LCR. That gives us an S squared The L's cancel, I get a 1 over RC, and then the R's cancel, I get 1 over LC. Is this the form of a high-pass filter? And the answer is yes. I have something times S squared in the numerator, and I have a second order denominator. So by association, then I can find omega naught, which is the square root of this term, so 1 over square root of LC. 1 times S squared means that H naught is 1. And then Q naught I can get from this term, so take the reciprocal of this term, which is Q naught over omega naught, and multiply by omega naught, and then we can get the value of Q naught. So this term reciprocal is just RC, and then 1 over square root of LC for omega naught. This is the same as our last calculation. So this is going to be the square root of C squared. It's going to cancel with one of these C's, and I just have R times the square root of C over L. Our next task was to evaluate the magnitude at omega equals to omega naught, and if that's equal to 1 over the square root of 2 times H naught, then the value of Q naught is equal to 0.707. So let's show that. So I went back to the class notes and I grabbed the magnitude from page 27. I'm going to set that equal to H naught over the square root of 2. So then I have H naught. When omega equals omega naught, I get 1 minus 1. That's going to be equal to 0. And when omega equals omega naught, I just had to have 1 over Q naught squared square root. The square and the square root cancel. I get a Q naught in the numerator times H naught. The H naughts cancel, and I then get that Q naught is equal to 1 over the square root of 2. Let's do the same for the magnitude of the high-pass transfer function. Back to the class notes in chapter 12 on page 31 and grab the expression for the magnitude. And I'm going to plug in that omega equals omega naught, and I'm going to set that equal to H naught over the square root of 2 and then solve for Q naught. So this is going to be equal to H naught over the square root of 2. Then my transfer function is going to be H naught over omega naught squared, and omega equals to omega naught, give me an omega naught squared. When omega equals omega naught, this becomes 1 minus 1, so it drops out. The ratio of omega to omega naught is 1, so then 1 over Q naught squared square root. This cancels with this. The square root cancels the square, and I just have H naught times Q naught. So now I can solve for Q naught. These are going to cancel here. Is equal to 1 over the square root of 2. Assuming our speaker can be thought of just as 8 ohms, then we can go back for our equation for Q naught, which is 1 over the square root of 2, and that was equal to R times square root of C over L, where now R is 8 ohms. Omega naught for our low-pass filter was at 750 hertz, so 2 pi times that would be equal to 1 over square root of LC. You can think of this as the square root of C over the square root of L. And I could solve for the square root of C as the square root of L divided by 8 square root of 2. And then from our equation for omega naught, we have 2 pi 750, and that's equal, you can think of this as the square root of L times the square root of C. So we'll have 1 over the square root of L, and then times the square root of C, which is 1 over 8 square root of 2 times the square root of L. And if I multiply these two together, I get the square root of L squared, so that's just equal to L. Put that over here, and then divide through by the 2 pi 750, and then the reciprocal of this would be 8 square root of 2. That turns out to be 2.4 millihenries. Now that we know the value of L, we can go back and get the value of C from this equation, square both sides of the equation, and then bring the C over here, and bring the 2 pi f squared, and then times the L. That gives me 18.76 microfarads. Likewise for the high pass, we had that Q naught was 1 over the square root of 2, and that was equal to R square root of C over L, and that we're looking at now a corner frequency of 6 kilohertz, so 2 pi times 6k would equal our omega naught, which is 1 over square root of LC. So from this formula here, we can think of this again as the square root of C divided by the square root of L. So bring this over here as the square root of L, and then divide by 8, that's our value for the square root of C. And from this equation, think of this as the square root of C times the square root of L, and we'll substitute in for the square root of C this term right here. 2 pi 6k, square root of L, 1 over 8 square root of 2, then times the square root of L. Multiplying these two, we get L squared square root. We'll put that over here as L. The reciprocal of this, that becomes 8 square root of 2, and then we've got this divided over here, which is 2 pi times 6k, and that turned out to be 300 microhenries. We can go back and solve for the value of C from here, square both sides of the equation, and put this over here, and I get C is equal to 1 over omega naught squared times L, and then plugging in 2 pi 6k squared times the 300 microhenries, I get 2.345 microfarads. Next, let's do the spice simulations of our crossover filters. So here's our low pass and here's our high pass crossover. I'll call this node 1 and 2, and then 3. We'll have the same input feeding multiple circuits. My inductor is between 1 and 2, and my capacitor and resistor are between 2 and ground with the values that we've solved for. I'm going to plot from 10 hertz 4 decades, and I'll do 50 points per decade, so I get 200 points. For my high pass circuit, my capacitor is between 1 and 3, and my L and R are between 3 and ground. We'll again treat the speaker as if it's 8 ohms. Remember that the impedance is changing with frequency. Take a look at the next page for the output. Plotting node voltage 2, given that our input's 1 volt and our transfer function then is just node voltage 2, and you can see I have a low pass, and then my 3 dB point was at 751.877 hertz, which is roughly what I designed for. And then for my high pass results, I plotted node voltage 3, because again my input's equal to 1, and my 3 dB point was at 5.9948 kilohertz, and we were shooting for 6 kilohertz. So my low pass and my high pass crossover are pretty much where I designed them for. I am using the exact values that I hand calculated, and we'll have to pick standard components eventually to build this circuit, and that will shift the filters a little bit, but basically we'll be crossing over at roughly the frequencies of 750 hertz and 6 kilohertz. Now let's go back and do the bandpass filter. Let's go back to page 9 and take a look at what the bandpass response looks like. For frequencies below 750 hertz, we begin to roll off the curve. So this part of the curve looks like a high-pass filter, and this part looks like a low-pass filter. If we were to combine a low-pass filter with a corner frequency at 6 kilohertz with a high-pass filter at 750 hertz, that could possibly make our bandpass filter. So let's go back and see if that would work. So I'll combine my high-pass circuit with my low-pass circuit, but now different corner frequencies. We could use our formulas to solve for the L's and C's, but now with a different value of our crossover frequency. For this high-pass filter now, instead of having 6 kilohertz, we're going to do it at 750 hertz. That gives me an inductance of 2.4 millihenries and 18.76 microfarads. Likewise, for the low-pass filter, I'm now going to have that at 6 kilohertz instead of 750 hertz. Plugging in 6K for the frequency, I get 300 microhenries and 2.345 microfarads. We'll take a look at the simulation just shortly, but is this going to work? One of the problems with interconnecting circuits, we worry about loading effects. Let's go back at lower frequencies around 750 hertz. Now notice that this L and C is much bigger than this L and C. So when we go back below the corner frequency, quite far in this case 750 hertz, the impedance of the inductor is going to look much smaller than the impedance of this inductor. So more like a short circuit. Likewise, the impedance of this capacitor is going to be a lot higher than the impedance of this capacitor, so more like an open circuit. From frequencies coming up to 750 hertz, we basically just see this C and L, and this looks like a short and an open. We just have our load of 8 ohms. So it's very much like the high-pass circuit that we analyzed, but in an approximation sense. Then as the frequency gets higher, the impedance of this becomes more and more like a short. This is more and more like an open as we get into the 6 kilohertz range. We just have then an LC filter with an R load, and that should be pretty close to our low-pass calculations. Let's see if this actually worked. Take a look at page 16. So here's my bandpass result. It was at node voltage 5. Comes up, comes back down again. Our corner's at about 748 hertz and 6.742 kilohertz. Again, there was some loading effects between my low pass and high pass in this bandpass filter, but I pretty much get that bandpass characteristic. And then I took a look at all of these plotted on one graph. And so here's my low pass at about 757, and that's going to run into my wide bandpass right about here. And then my high pass takes over, and I roll this off. So the low frequency speaker, the woofer is getting this range of frequencies up to about 757 hertz. The band pass is getting between 757 and 644 kilohertz. The high pass is getting everything above that. Now playing music through these 3 speakers, our ears will add the results together. So the results of the first speaker, plus the results of the second speaker, and the result of the third speaker, moving columns of air, our ear will then sense the summation of those 3. And that's how a crossover filter works. And this is supplemental problem 12.4.